And now, heat engines and not heat engines. For a heat engine, you need, this is going to be a schematic of 4 different types of things. There's the heat engine, and the heat engine has a, well, it's got a hot reservoir here, and that's at some temperature T hot. As we've seen before, the heat engine is dumping heat into a cold reservoir at some temperature T cold. And the purpose of a heat engine is to generate this right here. This will be the heat leaving the hot reservoir, and then there'll be some heat dumped into the cold reservoir. This is a waste because this is not coming out as work. And I'm just going to leave this here as this infinite cold thing, and this here is this infinite hot thing. But the point is, the balance between these two comes out as work. And we know that the work that's done by this heat engine is probably going to be, what do we say? We got to have conservation of energy, right? The engine's not storing up any energy. And so we're going to say QH is W plus QC, so then I could solve this for W and say, well, it's just QH, the heat leaving the hot reservoir, minus the heat being wasted into the cold reservoir. So that's the work there. And we had an equation for efficiency also. What did we say for the efficiency of this thing? We said that that efficiency will be, oh shoot, I guess it's, well, efficiency is defined as work out over work in, because if you work out, you win. And the work that we have to put in, is the heat from the hot reservoir, and the work that we get out is this actual, usable heat. So this could be coming out as mechanical work, or it could be coming out as electrical work, or what have you. But at any rate, we were able to go on with this and say that because the work is QH minus QC divided by QH, this is the same thing as 1 minus, QC, 1 minus QC over QH, and then Lord Kelvin helped us make that decision that that was the same thing as 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. So the efficiency cannot be 100%, and if we just take, let's just do this because you probably haven't done it, you slackers. If I say TC, the cold reservoir might be the outside temperature. I don't know, what do you want that to be? 300 Kelvin? Okay. And T hot might be inside of a gasoline engine, and boy, I'm just going to make this number up offhand. Let's say that that is 1,000 Kelvin. You can look that up and make fun of me in the comments if you want, but I'm going to find the efficiency. The efficiency of this engine would be 1 minus 300 Kelvin over 1,000 Kelvin, and that is 3/10, so this efficiency might be as big as 0.7. But unless you have a cold reservoir of 0, and we'll see in the third law of thermodynamics that that's not really going to work for you, you're not going to have an efficiency of 1. So, what do you think? Is the efficiency more dependent on the temperature of the cold reservoir or the temperature of the hot reservoir? You think about that for a little bit. So that is an engine, and all engines work via this schematic. I don't care how you're moving with your gas. Ultimately, you got to be doing something in a PV diagram to get that sucker to do work. You could go adiabat, and then, oh shoot, we're going to need to be going clockwise in order to do positive work. So you could be doing an adiabat, and then you could be doing an isotherm, and then another adiabat, and then another isotherm. And isn't that beautiful? And you could find that that sucker is doing some positive work for you that would be equal to the area that's inside of here. We're bringing it all together right now. Then, we want to consider not engines. And not engines are sort of exactly the opposite of engines, and I'm going to, on this page, discuss fridges. This is a refrigerator. Where did that D come from when they shortened it to fridge? Nobody knows. Maybe it's like the P in hamster that's not really there. So you need a hot reservoir, and you need, at some temperature T hot, and you need to have some heat. Oh, this is interesting. Well, you're going to actually have heat going into the hot reservoir, which we'll call QH, and that's not the purpose. You're not trying to heat up the hot reservoir, but let's say that down here, there's also some heat leaving a cold reservoir. Guess what? Heat does not want to leave a cold reservoir. So, this is the cold reservoir in order to make the heat leave the cold reservoir unwillingly. This is, strictly speaking, coming right up to the second law of thermodynamics and saying, nope, I don't want to do that. Because the second law of thermodynamics says the heat will never spontaneously flow from a cold thing to a hot thing. But if you do work, on the system, that would be this work that we're doing right here, you can get heat to flow from cold to hot. And that's what a refrigerator does. It pumps heat from a cold reservoir at some temperature T cold to a hot reservoir at some temperature T hot. So for the case of a refrigerator, this might be inside the fridge. And this might be outside the fridge. And so, if you then consider, well, there's a very, 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 very similar thing that many people have in their houses to a refrigerator, and I'll do that in brown because it's so similar. This sucker is called an air conditioner, and it makes you feel nice in the winter. Some people say that air conditioners have made humans weak and dependent on the cushy surroundings in order to survive. But an air conditioner requires a hot reservoir at some temperature T hot, and it requires some heat probably going into that hot reservoir. That's where you're just dumping all your extra heat. And then there's going to be a smaller heat, but it's flowing into the air conditioner, and it's leaving a cold reservoir. And that is where your table is. This is your house. And this is outside. And you know the second law of thermodynamics says that you can't, what does it say? It says something about you can't spontaneously have heat flow from cold to hot, so you know that there's some work coming in here. And we can say that the work, oh, maybe it's electrical power. Maybe you're getting some, maybe that work is, it could be the power, which is I times V. It could be I times V times time, maybe. Who knows? And the same thing with the refrigerator. You plug in the refrigerator, and suddenly it is sucking heat from a cold reservoir and dumping it into a hot reservoir, which is not what spontaneously happens, because it is, in fact, increasing the order in the room. So I'll start talking about order now, because that's going to be our next video. But we know that this is increasing the separation in temperature between cold and hot if we're dumping heat, to scooping it out of the cold reservoir and dumping it in the hot reservoir. And that's not what the universe likes to do spontaneously. The universe likes everything to be the same. The universe is like a giant lawnmower, and the first ones to pop up are the first ones that are mowed down. I'm just kidding. The universe is actually pretty cool. But we can investigate this work, and we could talk about something. See, the efficiency of a refrigerator isn't as well defined as the efficiency of a heat engine might be. I'm going to define something called a coefficient of performance for a refrigerator or for an air conditioner. And the coefficient of performance is about, it's kind of about like, it's about what you want to happen divided by how much you have to pay for it. So I'm going to write that. What we want divided by what we pay. And if I say what we want here, what is our actual goal? We're trying to cool our house, or we're trying to cool where we store the ham. And so what we want is actually the heat to leave the cold reservoir. And then what we pay is the work that we put in. Now notice the size of these two things. I didn't really draw them very carefully, but you know that QC plus W is equal to QH. And you know that, well, maybe you don't see it quite yet, but it's actually possible to put in less work than the heat that we remove, because energy conservation doesn't stop us right here. This is very interesting. Our energy conservation statement for the fridge and for the air conditioner says QH is QC plus W. So we could take this and plug it into our coefficient of performance equation. I'm going to go back to purple because I think that's working okay for us. So our coefficient of performance then could be, well, we could take this and we could multiply it. Sorry, I'm keeping on with my coefficient of performance. I need a little bit more room, don't I? All right, I'm going to take that room. I'm going to get some room right here. So I'm going to say that the coefficient of performance is, maybe I should change this numerator. This says QC, and I know that QH is QC plus W, so QC must be QH minus W. All right, is that okay with you? And then I'm going to divide that by work. And now I'm planning to divide, I'm going to divide the numerator and the denominator by, what should I divide it by? Let's divide it by QH and see what happens. I'm going to say this divided by QH and that divided by QH. And that won't change my answer at all, but as I distribute this funkiness right here, I'm going to get QH divided by QH is 1, and then I subtract W over QH, and then I divide that by W over QH. W over QH is kind of an efficiency, right? And you know that this, if we look at the heat engine, this is sort of the efficiency of the heat engine. That would be W is the work that we get out, divided by QH is the energy that we put in. But it's sort of, I have to put it in quotes. It's not exactly an efficiency here, but W over QH is kind of efficiency. So we can simplify this to be 1 minus kind of efficiency divided by kind of efficiency. And this kind of efficiency is going to have those same kind of bounds. It's going to be something like 70% or 30%, depending on the difference in temperature between these two things. And the beautiful thing about this is that the coefficient of performance can very easily be more than 1. A typical coefficient of performance, can I emphasize that again for you? You can take more energy out of your cold reservoir than the energy you're putting into your refrigerator. In fact, you can typically put in coefficient of performance might be somewhere between 5 and 6. That means that if you put in 1 joule, you could take 5 joules of heat away from the ham and keep that sucker cool. That's beautiful. Isn't that a beautiful thing? And we'll find a similar thing for heating your house with a heat pump. Let's go to that right now. The heat pump is another Knot engine. And you probably don't have one on your house. It's only practical in certain climates because it's all about heat difference, right? So here's your hot reservoir. Hot reservoir is right here, and we're going to have some heat going. What do you want? Towards it? Yeah, we're going to have heat going towards it, and that's QH, and this is at temperature TH. And we've also got some heat leaving a cold reservoir. And again, this is not spontaneously going to happen, so we'll have to provide some work going in. This is a T cold, and this is our work that goes in, and this is the heat that's leaving the cold reservoir. And again, we can make the same stupid statement of energy conservation that says QH is, well, that's the heat that's leaving the engine, so I guess we're going to have some QC coming in and some work going in. All right, fair enough, fair enough. So my point is, this cold reservoir in a heat pump is the outside air. You're taking a cold day, on a cold day, you're taking heat from the outside and bringing it into your house. And that does not spontaneously happen. You know, if you don't turn on your heat pump, your house is going to put heat into the outside. And that's annoying, and that's why we have insulation. But if you want to warm your house, you can put energy into a heat pump, and that sucker will then take the energy out of the outside and dump it into your house. Look at this. This is a large amount of heat entering your house. And that's a small amount of work that you have to do. So faced with two alternatives to use electrical energy to warm your house, you could either do some P is I square R, some joule heating, and you could say the work heating with joule, you know, like What I mean is, buy a bunch of toasters and turn them on, or buy those radiant heaters, or whatever those stupid things are called. Don't get me wrong, they're efficient in some applications, but generally, they are incredibly more wasteful than one of these suckers. Get yourself a heat pump is what I'm talking about, because the work of the heat here would then just be I squared R times delta T, the time that you're running that sucker. But if you get a heat pump, you can get a coefficient of performance for that heat pump. Let me define that sucker carefully for you. Coefficient of performance is going to be what we get, what we want, over what we pay. That's the way I like to think about this. And what we want is we want heat going into your house. So that's going to be QH. And then what we pay is this work. We don't pay for this heat that we're stealing from the outside. We pay for the work. And again, we see that we could have a coefficient of performance much greater than 1. And everybody smiles because now I can get 5 joules of heat in my house and only pay for 1 joule of electrical energy. That's awesome. Consider that for a little bit and buy yourself a heat pump. Stop burning gas. I guess that's about all I want to say there.